Hello, everybody. So what we're going to be looking at today is section 3.1 in your book. So we're in a new chapter, which is going to be vector valued functions and space curves. So yeah, uh, I'll resist the urge to tell you that this is a relatively easy topic and that will be done pretty quick because, I'm always lying when I say that. But here's what we're going to be doing today. So we are going to do what? Um, you know, define what a vector valued function is. Pretty straightforward. You will see. Um, you're going to, recognize parametric equations of a curve, which you've already seen parametric equations of a curve because a line is a curve. It's just not very curvy. So recognize parametric equations of a curve in space. Looks like a line, but it's not a line. We're going to learn what a helix is, the form of a helix, which is just a very basic curve that we can do that's not a straight line. I don't know why they list it, but they do as one of the topics. And we're going to talk about limits of these kinds of functions. I'll say vector valued functions. Okay, so let us get started. So, definition. Definition. So a vector valued function is a function of the form. And there's a couple of different ways you can do this, but depending on whether you're in 2 dimensions or 3 dimensions. So if you're in 2 dimensions, then there's going to be 2 components, right? So you just have some function. Now this is a real valued, this is a regular function, like, like sine t or something like that. Just a regular function that takes in a real variable and outputs a real variable. So that's like a scalar function here. So this is just a real valued function. But then you take that function and, it's multiplied by I, and then you have another real valued function, g of t, and that one would be multiplied by j. And in 3 dimensions, it's the same exact idea, except of course there's a I, a j, and a k component. So 3 components, x, y, and z component. Or you can write it in the other form of a vector, and you can use the triangular bracket notation and just say it's the vector f of t, g of t, or r of t equals f of t, g of t, h of t. So just like that. So it's very simple. It's called a vector valued function because the function itself is a vector, right? So you have these are, scalar functions, but you take them and you put the whole thing in together and you get a vector valued function. Okay, so it's a function where the output is a vector. And so that's easy to understand. We haven't seen these before, except in the concept of a straight line, and now we're seeing them in this concept, or now we're seeing them this way in general. Okay, so let's see here. Here's an example, something we can do here, just to make sure we understand. So if r of t, they like to use r, by the way, for curves. I actually don't really know why, but they like to do that. And let's just say 3 tangent ti plus 4 secant tj plus 5tk. Where you got that, and we want to find what? Let's say r of 0 and r of, where is this defined? I don't know. Let's just say pi over 4. Okay, so let's try to work this out. So this is just, making sure we can understand the concept of a vector valued function, that the output itself is a vector. So you just evaluate it the way you would any function. So if I'm trying to evaluate r of 0, that just means I'm going to take the equation and I'm going to put a 0 in for all of the t's. So I can say that it's 3 tangent 0 I plus 4 secant 0 j plus 5 times 0 k. Or if you want the triangular bracket notation, right, it'd be like 3 tangent 0 comma 4 secant 0 comma 5 times 0. Right, so use whichever notation you want. Of course, to evaluate this, you need to evaluate these all exactly if they're going to be trig functions. So if your calculator does not work exactly, then you need to use Wolfram Alpha or something that will give you exact answers for these. Probably 0 is easy, but maybe this one's, maybe the pi over 4 is harder. I don't know. All right, so what's tangent of 0? 0. So we have 3 times 0 times I plus 4 secant of 0. Secant of 0 is 1 over cosine 0. Cosine 0 is 1. So that's 1j. And then 5 times 0 is 0k. So you can write it that way. Or, of course, you can just go 4 times 0, comma 4 times 1. Oops, that should be 3 times 0, right? 3 times 0, 4 times 1, and 0. So what do we get? So we get 0i, 4j, 0k. So the actual output there is just 4j in that form. Or if you write it in this form, you get 0, 4, 0, right? Vector with length 4 in the j direction, but that's the same as that. So you don't do both of these, right? You just do one or the other depending on, which form you want, right? So you use the form you prefer, unless you're answering like a homework question and then you use the one that they make you use. But there you go. And point is that r of 0, they put the vector symbol over the r to let you know the result is supposed to be a vector. And keeping it straight in your head what's a vector and what's not a vector is really important in this class. So pay attention to things like the vector symbols, okay? So if we're going to do r of pi over 4, that would be 3 tan pi over 4 I, 4 secant pi over 4 j plus 5 pi over 4 k. So tangent pi over 4 is 1. So this is just going to be 3i. Secant pi over 4. Well, cosine pi over 4 is root 2 over 2. So secant pi over 4 is 2 over root 2, which is actually root 2. So you get 4 root 2j. And here we just simply get 5 pi over 4. Okay. So like that, or of course, in your alternate form, 3, 4 square root 2, 5 pi over 4. So whichever way you like. So those are examples of just how you would evaluate a vector valued function. It's probably exactly how you would expect it to work. Okay, graphing them. So let's see here. Blah, 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 blah. Okay, yeah. Okay, so sorry, just reading a little bit, see how they wanted to say this. So basically, a vector valued function, uh, a vector valued function with a single parameter like t defines a curve in space. So basically, what you do is you interpret the r of t vector. Remember, a vector does not have position. So r of t, like if r of t is like this right here, 3, 4 square root 2, 5 pi over 4, that has a direction and it has a length. It doesn't have a position. But we did have a standard position for vectors where we drew them all starting at 0, 0, 0. So you interpret the r of t as, let's see, as a vector in standard position, right? So that initial point is 0, 0, 0. And the terminal point traces out a curve in space. So, like, let's see if we can figure this out here. I'm not quite sure how to do it in GeoGebra. We'll find out. There's probably a way to make it. Why is ESPN open? That's weird. Start calculator in GeoGebra, graphing, 3D calculator. So let's see if we can put a curve on here. So we have to figure out how to do it. So let's see here. Um, tools, tools, more. Intersect, right? Segment, line, ray, vector, polygon, tangents, pyramid, circles, curves, parabola. Um, I don't know. Well, I wanted to show like some stuff on here, but maybe we'll just use Wolfram Alpha instead. Well, we could try it. Let's try this. I don't know if this is going to work. No, it won't. Let's just go Wolfram Alpha. So if I'm going to plot this here, which, you can barely see it there, but I'm going to try to plot like R of t. You don't have to call it R of t, but I just am. Equals, and they like to use curly braces, but it doesn't really matter. I'll use regular braces here. 3 tan t, comma, for secant t, comma, 5t. So let's see if it understands it first of all. It does. So you can see that it did interpret it as a vector valued equation. Did it do anything with it? No, it didn't. Let's say we can say plot. See if that works. There we go. Oh, that's terrible. That's not a 3D plot. Plot 3D. Try that. Plot 3D. Go. If this doesn't work, we'll find a different tool. I just didn't want to Google for the tool. You can do it with Wolfram Alpha. Okay, that's useless. Okay, so parametric space curve. Wolfram. This should do it. Nope. Life is hard. I guess, okay. You know what? We can try it. So, direction, parametric, plot, 3D. I don't know why I didn't do it. Okay, hold on. We're going to try it. Okay. Wolfram, plot, 3D, parentheses. And it was just like this, right? So, like, let me just try this. 3T, T, 2T. See, it doesn't work, even though we just followed the thing. We didn't do. Okay. Well, I'm not restarting this. Okay, so parametric curve. I really wish I was on a computer now because it's easy to plot on a computer. All right, we'll do this. Parametric curve graph for 3D. I didn't want to use this site, but this is good actually. So you can see what's going on. So if you look at, can I put the cursor somewhere? Hold on. I can't. But if you look at this little meter, I don't, you can see it. Yeah, you can. That's going up, like it goes to like this meter right here. Um, that is t, and so t is moving. Make small. Make small. Take up less space. Very frustrating. Okay, so t is increasing and tracing out that curve. And so you can change the functions for x of t, y of t, and z of t, and you can plot your curve there. So I can come up here, delete this, and so what did we have? We had, I don't know what one we plotted, but 3 times tan t. The other one was 4 secant t, 4 times secant t. And then the last one was 5t, 5 times t. That, okay. How do I make it start now? Function A. Redraw. Is it calculating it? Well, we failed. We just crashed it. That's what we did. Well, fantastic. I swear we can do it in Wolfram. I just need it to bring up the thing here. That's what I was Googling for. Wolfram curve in 3D. 3D plot. Yes, I know 3D plot. Parametric plot 3D. That would have worked. Okay. Parametric plot 3D. Parametric plot 3D. paste, paste. That's not what I want. We're going to give up in a second here, especially since I typed it in wrong. Okay, we'll try it. Okay, so their examples here, they have a square bracket. So we're going to use a square bracket. We can do this, okay? We can do it. Square bracket. Then we type in curly braces our function. Oh, two sets of curly braces. Awesome. That's like too much effort here. I'm going to do one set of curly braces. T, T, T. I'm going to see what this does first of all, and then we're going to edit it to make it actually work, because I don't think it's going to work if I just type that in. Because I feel like we've already tried that. Oh no, it worked. Of course it worked. Okay, so parametric plot 3D is what we want. So we can change this to our curve, which was, I don't remember now, but I'm going to say it was 3 times tangent t, comma 4 times secant t, and then 5t, right? Comma 5t. Close that, go. And we'll get a plot, and it's not going to be a good plot or anything because this curve, they didn't intend for you to actually try to make a plot out of it, so it's not a pretty plot. It's got, tangent and secant are both discontinuous in certain places, so you have like holes in the graph. But point is that it's some kind of curve. And if you come up here and you just change the functions to some other function, like I don't know, x squared. Nope, not x. T squared, like that. You can just see what the function looks like. You get a different kind of function there. If you come up here and change this to just like 4, you get a different kind of curve, and so on. So that's not animated like the other example that we saw, but this still works. And I don't remember what it said about why did it go back to the beginning. Why did it go back to the beginning? Okay. I don't remember what it said about the parameters. Okay, u, min, max. So I think we can do this. We'll try it. If I go t0, 5, we might get it to plot for certain t values. Not guaranteeing that's the right syntax, but we'll find out. Nope, absolutely not. U, min, max. Should have worked, didn't work. Well, awesome. So, I mean, those are not good tools. I guess we're doing it by hand. Back to our note app. I'm gonna have to close it again, aren't I? Yes. All right, so that was a lot of wasted time, so sorry about that. I'm not cutting this from the video because that will make the video take twice as long to post. Let's go. All right, so point is that you kind of saw a vector trace a curve. So like if you had a curve like this, I'll just do this one by hand. Example, R of t equals, let's say, 3 cosine t, comma 2 sine t, comma, let's just say 3, right? And then I'm going to give you, I'll say 4 t, and we're just going to go between 0 and pi. Okay, so like what would that be? So if you think about it on a 2D plot here, that's a 3D plot. On a 3D plot here, you've got z, x, y. Then what's going on here is if you think about plugging different t values in, right? Like r of 0, for example, if you put that in, is going to be, so I'm putting in 0 here. Cosine 0 is 1, sine 0 is 0. You would get 303, right? That's a point in space. If you put in like r of, let's say, pi over 4, then you would get 3 root 2 over 2, 2 root 2 over 2, 3. If you put in like re is r of pi over 2 is what I meant, pi over 2, then you're going to get 0, 2, 3. If you put r of, let's say, 3/4 pi, then cosine of 3/4 pi is going to be negative root 2 over 2. So you get negative 3 root 2 over 2. Sine of 3/4 pi is going to be positive root 2 over 2. So you're just going to get root 2 and 3. And if you go r of pi, you're going to get 3 cosine of pi. It's going to be negative 3. 2 sine of pi is 0, so you get 0 and 3. All right, so what was the point of that? The point of that was as follows. So if I draw a great big plane up here in space, and let's just say that this intersects right, oops, that's fine. Just trying to draw it so it's more visually easy to understand what's going on here. So let's just say I drew this plane up at z equals 3. Okay, now that's not the curve, but the curve lives at a height of 3 because if you look at the y value or the z values, 3, 3, 3, 3, 3, right? The z value is always 3. So we're up here at z equals 3. And then if you go and you plot these points, though, then what you get is that, put some points on here. That doesn't look right. Let me change this curve here. Okay, that looks a little better. So if you try to plot these points here, then they're all in that plane that I drew. And so like if we try to plot 3, 0, 3, where is that? That would be 3 on the x-axis, 0 on the y-axis, 3 on the z-axis. So you would just get a point like that. And that'd be like r of 0. Now, if you put in r of pi over 4, then you get this point here, 3 root 2 over 2, 2 root 2 over 2, which is root 2, comma 3. And that would be hard to draw, but somewhere in here, in this plane. Then r of pi over 2 would be 0 on the x-axis, 2 on the y-axis. Y-axis is here, so along this line. And 3 on the z-axis, because we're up. So like there. R of 3/4 pi. Now the x value is negative, but the y value is still positive, so we're still on this half. And the z value is 3. So that's like back here somewhere. And then finally, negative 3, 0, 3. Negative 3 on the x-axis, so that's back this way. 0 on the y-axis, so we're not this way or this way. We're right here. And 3 on the z-axis, which means we're up in this plane like we already knew. So like right there. So what you get is this kind of shape, right? And technically what's going on here, if you want to interpret it in terms of what I said here, I said you interpret r of t as a vector in standard position, initial point 0, 0, 0. The terminal point traces out a curve in space. So technically what happened was, what r of t actually does is it points from 0 down here up to here. That's r of 0. That's too hard to read. I was trying to pick a light color, but that's too hard to read. So like that's r of 0. This is r of pi over 4. This is r of pi over 2. And then you got that one and that one. So actually, technically what's happening is you've got this vector And as t is changing, this is tracing out this curve with the tip of the arrow is tracing out this curve in space. And so we don't care about the actual vectors, right? Like I didn't plot 303 as a vector to get the blue curve. I just plotted 303 as a point, which was this point. This point, if you interpret it as a point, not a vector, here it is. If this is a point, not a vector, here it is. Right? So like 303 as a point is right here. 303 vector is from here up to this point. So that's what we're talking about when we say vector in standard position, the terminal point traces out a curve, right? The terminal point is where the arrow ends, and that's tracing out this shape in 3 dimensions. Okay, so that was, I should have just done that from the beginning rather than trying to plot it. I really thought that we would be able to get like a graph like this one without too much trouble, but alas, didn't happen. So those are space curves. We saw how to plot one, and you can also draw a direction arrow on these because like time started at 0 and went up to pi, so started at this point and went to this point. So you can draw an arrow in the direction that the curve is traced. Okay, so we did. And you don't need those green lines for the vectors for anything at all. Okay, so that's how you would graph one, is you just plot a set of points and then you calculate the vector at a bunch of t values, and then you plot them in 3D space and then connect the dots with a line. Okay, maybe we'll even say that that's what we did just so we know. So the steps to plot were this. So a curve r of t over t in between a and b, right? So what did we do? We evaluate r of t at a number of points, number of t values, starting at a going up to b. You interpret the results as points in space. That is, like if r of 0 is like 1, 2, 3, right? That's a vector. You plot a point at the point 1, 2, 3. Right? So parentheses there, right? So I said interpret the results as points of space. That is that. So, plot all those points. In space. And then what you can do is you can draw a direction of, you can draw an arrow for the direction of travel along the path. Indicating the direction from, R of A was somewhere to R of B, which is somewhere else. Okay, so that's what we did. We did all of that, right? We plotted these points. We drew the arrow, right? This was the R of 0. This was the R of pi, and we went along the curve that way. Okay, and that's how you would plot a space curve. Now, next thing we want to talk about are limits of space curves. and then we'll look at some specific curves to try to get better at doing any of this stuff. So limits of vector valued functions. Okay, so in practice, this is easy, like, easy in quotes though, right? Nothing's easy. But in practice, this is, easy in the sense that we don't really need any kind of new definitions. We're going to have a definition, but basically, you're just going to evaluate the limits of the individual pieces. So in practice, this is easy because like R of t equals f of t, g of t, h of t, right? That kind of space curve will be evaluated as follows. Piece by piece or component by component is how I should say it. So like if you needed to do like the limit as t goes to like, I'm just making up a number here, right? So let's just say 3 of r of t. What you're actually going to do is you're going to do the limit as t goes to 3 of f, the limit as t goes to 3 of g, and the limit as t goes to 3 of h. So that's not going to be really like, making you think super hard. It's just that you'd have to do 3 different limits in order to do this. But in order to justify this, we need to specifically say what we mean for there to be a limit of a space vector valued function. And then after we have a definition of that, then we can justify this kind of reasoning, right? So I'm just letting you know where we're going to end up before we start. So let's do that. So according to your book, here's the definition of the limit. I say according to your book because I'm going to point out what I think is an issue with it. But a vector valued function R approaches the limit L, which is also a vector because it's a vector valued function, as t approaches A, written, how do we write it? Well, you actually saw how to write it. The limit as t approaches A of R of t equals L, right? So just write it the way you normally write limits, provided the limit as t approaches A of magnitude R of t minus L equals 0. Actually, I lied. I said I was going to have an issue with this definition, and I realized that I don't. I think it's okay. So what this is saying is that, what this is saying is as follows. I'm going to try to draw a picture, okay? So like, let's just say you have a curve in space. Okay, so that's just a curve. So that's just going to be R of t. I'm just drawing it in space. Okay, now L is actually a vector. So it's you can think of it as being a point on the curve, right? It's a vector, but from 0, 0, 0 up to L, 0, 0, 0 up to the point on the curve that corresponds to L. So like you've got this like point here, let's say that is L. Okay. So what they're saying here is they're saying that when t is going to A, then when t is going to A, the distance from L to the point on the curve has to go to 0, right? So basically what they're saying is like if you've got a point like R of t on here, then this point ends up having to slide over to there, as t goes to a, right? Because this is the magnitude of the difference of these two things. So if the magnitude of these two things goes to 0, that means the point on the curve must be sliding over to where that L is. So that makes sense for a definition. But the reason it's not the same as the old definition of a limit that you had was the old definition of limits involved absolute values, right? This doesn't involve the absolute value. This actually involves the magnitude of a vector, right? Because this is a point or a vector, a three-dimensional vector. This is a three-dimensional vector. How do you say these are close together, right? The way that you say they're close together is you say subtract them and take the magnitude. That should be small. That means these two vectors are close together. So if the limit as t approaches a of this goes to 0, that means that as t is going to a, the r of t is sliding over to where that L is. And that's a limit. Okay. So the main thing to notice about this is that this is not this, right? Like this is three separate limits component by component, and this is one single limit that's not component by component. So I don't think we're going to prove it. I don't think they prove it, do they? They sort of do. No, they just say it. They just state it. They don't prove it. But the idea is this. So according to this definition, for the limit to exist, then, right, you've got this, where is it? Sorry. The limit as t approaches a of the magnitude of r of t minus L has to equal 0, right? So if I just write these out, so if your r of t is f of t, g of t, h of t, so we have three functions, and our limit, we need to know our limit. So let's just say L, let's just say that the limit is just ABC. We could have used like L1, L2, L3 or something, but just use ABC. Then this limit right here is the limit as t approaches a of the magnitude of, oh, actually, let's not do that yet. Sorry. Of the magnitude of r of t minus L. So that's the vector f of t minus a, g of t minus b, h of t minus c. That magnitude is supposed to be 0. Now, how do you actually do the magnitude of a vector? That is the square root of f of t, in this case, the x component squared, plus limit of the y component squared, and the limit of the z component squared. All of that has to be equal 0. Okay, and I don't really want to do the proof here, but if you think about these three quantities here, this is positive or 0, right? This is always greater than or equal to 0. This is always greater than or equal to 0. This is always greater than or equal to 0. So in order for all of this to end up 0, this thing which is positive or 0, this thing which is positive or 0, this thing which is positive or 0, you add them up, you get 0. The only way for that to happen is if all three of these individually work out to 0. Okay, so this can only happen if individually you have the limit as t approaches a of this thing is going to have to be 0. And I want to say that 3 times. So I'm going to duplicate it. And then I'm going to duplicate it again. And just change the numbers inside. So this and this. Those all have to end up 0. Okay, but if all 3 of those end up 0, that's only going to happen if, like if you square root both sides here, that would only happen if you square root both sides. If that's 0, that's 0. Oh, oops. I just realized that I can't use A for this, can I? Okay, here's we're gonna fix my issue. A hat, B hat, C hat. 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 That way, this A is not the same as this A. That's why I'm doing this. A hat, B hat, C hat. That equals 0. Right? So basically all I did from here to here is I just square rooted both sides. And you have to remember that when you square root something squared, you actually get the absolute value of that thing, right? Because if A was started out negative, like imagine A is -5. -5 squared is positive 25, and the square root of positive 25 is positive 5. So like if you do this, just writing what I just said, you actually get positive 5, which indicates that like this operation here actually absolute values whatever's inside. So that's why this, if you square root both sides, it turns into absolute values, not just like parentheses, for example. Okay, so you do this, and this is actually the definition for the limit of f of t to be a. So this means that the limit as t approaches a of f of t must be a hat. The limit as t approaches a of g of t must be b hat. And the limit as t approaches a of h of t must be c hat. Okay, now technically we didn't do the proof, but we did most of the proof, right? So imagine if you started with this. Suppose this limit is A, this limit is B, this limit is C with caps. If this was true, this would be true. If this is true, this would be true. And if this was true, then this would be true. And if this was true, then this would be true. And if this was true, then this is true. So you'd have to redo this work backwards if you wanted to do the proof that this thing and these things were the same. But I don't want to. Also, the thing where I pulled these out individually, I didn't really justify that with a formal mathematical reasoning. So this isn't a real proof anyway, but it's really most of the idea. So that's what you do. So without a real proof, theorem, the limit as t approaches a of r of t is the limit as t approaches a of f of t, comma, the limit as t approaches a g of t, and the limit as t approaches a h of t. Given r of t equals f of t, g of t, h of t, and assuming the limits exist. Okay, so that's the theorem that you use. So you just do, when you're trying to do the limit of a vector valued function, you just do the limit of the individual pieces. Now that's a lot of work for really not a lot. So like, here's an example this is from the textbook. Calculate the limit as t approaches -2 of r of t, where r of t is equal to square root, parentheses, t squared minus 3t minus 1i plus 4t plus 3j plus sine t plus 1 pi over 2k. And so what you would do is you would just say that that limit, t approaches -2 of r of t, you do with 3 separate limits. And, I don't want to keep doing this, but for this one, I'll do it. So you just put that first function in a limit, and then I, plus, and then you do a limit as t approaches -2 of the second function, j, and then you do the limit as t approaches -2 of the third function. Okay, so 3 separate limits, and these 3 separate limits are really simple. You're just going to be plugging in the -2, right? Remember, for limits, if you can just plug in the number because it's a continuous function, that's what you do. You just plug in the number. So there's not really going to be a lot to it. So you just plug this in, plug in t equals -2. That's all we got to do to evaluate these limits. And we'll get what we get. So we got put in -2. You have 4. 4 plus 6, because that's a minus. So minus minus be plus. So 4 plus 6 is 10, minus 1 is 9. So it's square root 9 I, which is obviously 3. Here, put in the -2. So -2 times 4 is -8. -8 plus 3 is going to be -5. So -5j. And then here you put in a -2. You have -2 plus 1, which is -1. So negative pi over 2. I lost the sign, I realize. Sign of all that. I got to rewrite this. Okay. So you put in the -2. -2 plus 1 is -1/2 pi. So negative pi over 2. Sine of negative pi over 2 is -1. And so what do you get? You get the vector 3, -5, -1. And that's it. That's what you do. Okay, so you can write it that way. You write it that way. Whatever. So those are limits in 3 dimensions. Let me look at the things. Limits and continuity. Okay, we didn't talk about continuity. Oh, okay, good. They do mention it. I could have sworn that they were asking questions about continuity without actually telling you what continuity was. But basically, the definition of continuity is the same as the definition of continuity from Calculus 1. So just written with the symbols here. So what? Oh, okay. They just write it for 2D or 3D. So they'll say r of t, let r of t be a vector valued function in 2D or 3D. I'm not going to write it both ways. In 2D or 3D, doesn't matter. You can actually extend it to as many dimensions as you want, I suppose. We would say that r of t is continuous at t equals a if, so 3 things happen. You need the function value to exist. you need the limit to exist, and you need the function value and the limit to be equal to each other. Okay, and that's exactly the same definition as you have for continuity in functions of one variable, scalar valued functions, real valued functions. Okay, so let me just find a question involving continuity here, so we can talk about it. Uh, well, where's one that's we can use here? Okay, dumb. Okay, so let's do this actually. So I'm going to give you a vector valued function. Here it is. We're going to go r of t is equal to 2e to the negative t I plus e to the negative t j plus ln t minus 1 k. So you got a natural log in there. And what I want to know are two things. One, I want you to find the domain of the function, right? What is the domain of r of t, right? So basically what t values are allowed, right? The same as the domain of any function, okay? And then B, I want to know for what values is r of t continuous. Okay, so let's do these separately. Start with A. So A, a different color, darker. Okay, so let's see. What is the domain? So basically what you're going to do is you're going to look at the three different parts and you're going to decide which t values are okay in all three functions. So you look at 2e to the negative t, e to the negative t, and ln t minus 1, parentheses, and figure out which t values are allowed for each of those. Okay, so 2e to the negative t, you can plug in any t value you want. So all t in negative infinity to infinity are fine there. E to the negative t, all t in negative infinity to infinity again, they're all fine. The natural log, that's where you've got a function that is not always defined, right? So what do you do there? Well, you know that for a natural logs are only defined for strictly positive values. So this is for all t with t minus 1 has to be positive, which means that if you move the 1 over, t has to be greater than 1. Okay, so combine the information here because the domain has to be, to be in the domain, all of these must be okay. Like you must be in the domain of each of the three. So the domain of r of t must be t greater than 1, right? All three components are defined there. Okay, so that's how you would find the domain. It's just the domain of each of the individual ones and then combine the information because all three, you need to be in the domain of all three to be in the domain of the R of t. So that's the domain, not too bad at all. And then for continuity, you just think individually about the continuity of the components as well. So since limits, the limit as t approaches a of R of t comes down to the limits of the pieces, which are, what are they? 2e to the negative t, e to the negative t, ln t minus 1. You need to figure out where each of those is continuous. Understand continuity of those three. So 2e to the negative t and e to the negative t are continuous everywhere. Right? Like if you plotted them on a t graph, like a t and function graph here, like you put t here, you put just like y here. Not the y component, but just like, I'll say f of t. Like if you plot them here, they're both just exponentials, so they just go like that, right? They have that same kind of shape. And the natural log ln t minus 1 has graph. That's a bad way to plot it. Hold on, let me just erase that. So normally the natural log graph has this kind of shape, but normally this vertical asymptote is over at 0. The fact that it's got the t minus 1, that's moved the asymptote from 0 over to 1. So this is at t equals 1. So that's also continuous as long as t is greater than 1. Greater than 1. So again, we take this information overall and we conclude that R of t is continuous for t greater than 1. And you can say that however you want, right? You could say like from 1 to infinity, or however you want to say it. Okay, so that's how you would do continuity and domain. It's just same as continuity and domain of any function. So those are those. Now, interestingly, this learning objectives that we had at the beginning here, we listed these things, and if I'm not mistaken, they do not actually plot. They do not do the plot of a helix in the section. Like I didn't see a plot. We're still going to plot one though. So basically, a helix is going to be this. So let's do helix. Helices is how I should say that. Helices. Helices. Plotting a helix. Okay, so from, let's say, Calc 2, maybe, I'm saying Calc 2, but maybe you know this and maybe you don't from Calc 2. You have learned to plot circles, parametric equation of a circle. Of a circle with a certain radius. radius r. And this is how they were. You would say like x of t equals r cosine theta, cosine t, and y of t was r sine t. Now, don't get this mixed up with polar coordinates. These aren't like the polar coordinates conversions. These are actually just equations for plotting a circle. They just look the same because polar coordinates have, something to do with circles. So what's going on here is like if you plot like x of 0, y of 0, right? Then actually, let me just do this. So like if I say like x of t, y of t, right? If you do that, like let's say that's r of t. If you do r of 0, you get r cosine 0, r sine 0, which is simply r comma 0. And so you get a point here on the x-axis at r. There's a difference between the vector r and the radius r, right? One's a vector with a hat and one doesn't have it. If you do like r of, let's say, pi over 4, you get r cosine pi over 4, r sine pi over 4, which is r root 2 over 2, r root 2 over 2, which I'm not really going to plot very carefully, but it's like somewhere in here. So I think this is, it's just a point there. If you plot, I'll say r of pi over 4. And if you keep going here, this is where r of pi over 2 would be. This is where r of pi would be. Down here is where r of 3 pi over 2 would be, and so on. And so what happens is you've got this come on, I'm just trying to move you to match. Okay, so you got this circle like this that goes through the points. I'm amazed that that dot is actually on the curve, by the way. You get this circle and it's traced out this way, right? Going around the curve, starts here. So you get this circle, and that's what these equations would be, right? Equations of a circle. Now, if you imagine a curve in 3 dimensions that looks like this, the definition, the curve, let's say r cosine t, r sine t. So the x and the y components are going to make circles, but then on the z-axis, we just have something like kt. Then what happens is this. So you got a 3D plot. So the curve defines a helix. Well, I mean, that's just it. It defines a helix. There's nothing to say about it. It's really nothing to it. If you look at the plot, though, that's what I want to do. So if you look at a plot of this function, x, y, z. So if you have this kind of curve here, as t is increasing, the x and the y components are making circles. So like you could think of it just like this, right? It starts here and then goes around and comes back, right? So we just do this. That's what this does. But what's happening here is while it's going around in a circle, the z value is increasing. So instead of just doing this in the xy plane, it's going to go make circles while it's climbing up. So it'd go like this, spiral up. So your helix goes, let's pick a different color. Let's go pink. So it starts there, but then I just bump my hand there. I got to do that. Oh man, delete the whole thing. Right? It does that because as it's making circles, as r cos t, r sine t makes circles in the xy plane, the z value is increasing. Kt is going up. And so the result is that spiral shape. And also, maybe I'll highlight this. Oops, that's not a highlighter. Maybe I will highlight it like this. Also, you can kind of see that the spiral is kind of like on a cylinder. It's like the outside of a cylinder. Okay, so that's a helix, right? So you can recognize them by this kind of thing happening. A cosine for one of the variables, a sine for another variable, and the third variable is just a constant times a t. Okay, that's about all there is to say about them. They're helices. Helices, you can define them in terms of, a lot of different ways. Example, I could say like plot, let's say x and z. Let's say like 2 cosine t, t 2 sine t equals r of t for t in between 0 and, let's say, 4 pi. Okay. Like, what would that look like? So you could work out the values, but if you know something about how this is supposed to work, we should be able to figure it out, basically. Right? So first of all, let's figure out where we start. So put a 0 in there. What's r of 0? So you figure out what r of 0 is, you get 2, 0, 0. So that's like here. Okay. Now in the xy plane here, let me try to draw the xy plane. Sorry, the xz plane. So in the xz plane here, this should be lower. Sorry. In the xz plane, the x and the z are tracing out circles. So that would be like, right, like tracing out circles like that. But while that's happening, the z value, or sorry, actually the y value, right, should be increasing, heading that way. So instead of having those circles stuck in that plane, what you've got is the y value is coming forward. And it's hard to plot, but something like this, right? Coming out this way. Now, once you have the basic idea there for what's happening, also how many circles is it making? Well, this is t between 0 and 4 pi. You should know that 0 to 2 pi traces out one circle. So like from here to here, that's like this is r of 0. This is r of 2 pi. And then the next one here, that would be r of 4 pi. So you'd actually have to stop the curve there, which means I'm going to have to redraw it, I'm realizing. Okay, that's not that bad. So it would be this much, that much of the helix. So making circles, but only 2 of them. And, it could go forever out that way, but not with these t values. And traces out that way. Okay, so those are helices. Just a spiral, basically. And yeah. Okay, so I think that's it for this lecture. Space curves, just basically down to it's a function with an x component, a y component, and a z component. and you've got a single variable, t, single parameter. If it has two parameters, you actually are defining a surface and not a curve, which is why I was careful up here to say, uh, where did I say it? Well, I didn't. Oh yeah, here's where I said it. Single parameter t. And that's because two parameters would give a surface, not a curve. So we'll cover those later on. All right, I think that's it. So I will talk to you guys next time.